said last time, and then continue our discussion. So what we did, we saw that if you have a p-n junction, and what you had in a p-n junction were two pieces of silicon, a p-type semiconductor and an n-type semiconductor. And the way they are formed is you never, almost never, take a piece of p-type and take a piece of n-type semiconductor and then attach them to each other to form a diode. Because if you do that at the junction, you will have these impurities in the lattice structure that will create a lot of trap sites. And they will not be very nice because a lot of your carriers will be combining there. The way you actually form them is that if you make them out of one solid piece of silicon and you introduce dopant through the diffusion process, not the diffusion like the electron, actually you introduce the dopants at very high temperature and they diffuse into the lattice. They become part of the lattice. So when you do that, different kinds of dopant diffuse and then you do it at different times, so you can actually first dope it up to here with n-type material and then dope it on a little shorter time and you get the p-type material. And we'll talk about how it's done later on in more details. So now when you have this thing, and we saw when you form this, if you have an n-type and p-type region on both sides, what you form is a region which is pretty much depleted of charge, of free carriers, electrons and holes. And as a result, because of the fact that you have the ions left behind, so you have the positive ions left behind here, and the negative ions left behind on the other side, you have an electric field, in this case pointing in this direction. In other words, there's a built-in potential barrier, right, when you do that. And we saw it in the energy band diagram. What you saw was something like this. So you had a p-type, and then you have the n-type. And then what you have, well, of course the band gap is constant throughout, so it's a good picture. Now, and one question is, what is the height of this potential barrier? Let's call it, well, in voltage it would be psi, so in energy it would be Q psi naught. If it's the built-in voltage, it's psi naught. What is this psi naught? How do we calculate it? Let's say I give you this, and you say, well, the doping concentration on this side is Na, the doping concentration on this side is Nd, the donor and acceptor levels, and what is the built-in potential? How do we calculate it? And room temperature, of course. We saw that at 0 Kelvin, at absolute 0, there would be no built-in potential, because none of these are ionized. But these energy levels, you have these acceptor energy levels, and the donor energy levels, and these are not ionized at 0 Kelvin, but at room temperature they are. So let's say we are at room temperature. So how would we go about calculating the built-in potential if I ask, which I have?
ET log of AND over NS.
Yeah, but how do you arrive?
No.
That's even worse, right? Knowing the answer without knowing the logic. I mean, I'm not saying that you don't, but I'm saying it's even worse than not knowing an answer. But I'm sure you do. So how do you arrive at that?
Honestly, I don't know. It doesn't explain.
Okay, so let's talk about it. Okay, so where does it come from? So what is the doping? So let's go back at the concept we have. We could calculate the N, the concentration of electrons on this side, and the concentration of the holes on the P side, right? How do we calculate them? What were they? We had expressions for it, right? In terms of Ni. We derived them from the distribution. We use the Boltzmann distribution approximation. So how did we arrive at N? What was N? Was Ni was the intrinsic concentration times E. So the difference of the Fermi level and the intrinsic level, whatever the intrinsic level is. So let's call this EI on the N side and the intrinsic level EI on the P side, right? So we derived this expression. You remember this? Right? And the same thing for the P side, which was the opposite. So it was EIP minus EF over KT. You remember these two, right? You agree? Did you agree with these? We derived these, right? Last time. So we came up with these two expressions, and what I wanted to find out is really what is the quantity I was trying to find out? What is this? This Q psi naught is really nothing but the net energy difference between the intrinsic levels. So this is Q psi naught. Right? The energy difference between the left and right hand side. Because the intrinsic level is the intrinsic level, whatever it would have been. So the difference is equal to the difference between the energy levels. So I'm trying to so basically Q psi naught is nothing but EI P minus EI N. And of course that's in equilibrium, thermal equilibrium, so the EF is constant all across. So it's the same EF on both sides. So if I have these two, can you think of a simple way I can arrive at the relationship between these two? What if I multiply both sides of this equation? So I multiply both sides, I get N times P. Well, but remember, this is N on the N side, and this is the P on the P side. So it's not that N times P is going to be Ni squared. The fact that the product is Ni squared is valid at any given point. But it's N on this side and the P on the other side. So actually, let's talk about that for a second. What is the P? What is the concentration of holes on the P side at room temperature? Na, exactly. So I know that all of my acceptors will be ionized at that level, and we saw that nice little curve, right? The temperature that we went up first, and it became flat, and then it went up again. So we are in the middle range. So that's the beauty of it. So I can control this. Oops. Well, this is Na, and the same thing for the N side. This would be Nd. So from this point on, instead of writing it this way, I can actually multiply these two and these two. So I get Na times Nd, which is Ni squared, and multiply these exponential, I get the sum of the arguments, right? And the EFs cancel, so I get E2 EIP minus EIN divided by KT, right? And you can see where we're going. I know this is Q psi naught. So psi naught would be KT over Q, natural log of Na Nd over Ni squared. So that's where it comes from. So if I ask you what is the delta potential, you can easily calculate. All you need to know really is the doping level for the P side, doping level for the N side, intrinsic energy, intrinsic doping carrier concentration in the semiconductor. These are the three things you need, and the rest of them, of course, you know. Okay, and then of course you need to know what temperature you're at. And you can see there's a direct relationship to the temperature. Even from that expression, you can see as you raise the temperature, this goes up, but of course this one changes too. This is a strong function of temperature, because this is temperature reduced. So you have to take it into account. Okay, so that was the built-in potential, and that's fine. And then we applied forward bias. When we applied reverse and forward bias, and we saw, well, even in the case where there is no bias, there was a distribution of electrons here and distribution of holes, which we approximated using the Boltzmann distribution. So there are some of them, they're moving randomly, right? Thermal energy. They have the electrons on this side and the holes on this side have thermal energy. They're moving randomly. And every so often, one of them has enough energy and is moving in this direction so that can cross. And the remaining ones are bounced back. So the number that can cross is proportional to minus Q psi naught over KT, according to the Boltzmann distribution. Now, when I apply a potential, an external voltage, or an external potential, like a forward bias in this case, Vd, I lower this potential barrier, right? I push it down. So when I push it down, this is what's going to happen. So I lower this potential barrier on this side, lower this one on this side, and what happens is that in addition to those guys who could pass, now a whole new bunch of guys can pass, and these guys can pass, and these holes can pass across the barrier, because now the barrier is lower, now there are more people, more electrons and holes who have enough thermal energy to cross. And it's purely thermal. This process is purely thermal. No fancy transient stuff here. It's a very simple concept, and that's why it's so effective and so fast. It is thermal. So these guys can pass, and we saw that these new guys are proportional to E Q psi naught minus Vd, KT, and then therefore you saw that the net current is proportional to E2Q. And so basically the net current, when we calculated it, was Q Vd over KT minus 1, and the proportionality constant we call Is. So the dipole current in forward and reverse mode of operation could be given by that expression. Alright? Which which shows you why it's a rectifying junction, because in the reverse flow, the maximum current that you can carry is minus IS, and minus IS is usually a very small quantity. Okay. So that was the diode. Now, these carriers were injected. All you did to control the amount of net current that flew, it was just basically lowering the potential barrier. Okay, now, then we said, well, this is a nice thing if you want to make a rectifier, but there's not a whole lot of things you can make with this. For instance, and you could try to make things like gates with this kind of with a diode, and there is a logic family that uses diode, but it's kind of not very effective because first of all, it doesn't have a whole lot of gain, and the fan out is low, and all those things. So you need to start thinking about how we can make a three-terminal device, because whether you want to make it a digital circuit, a gate, or an amplifier, what you really need is a device whose current or voltage at one terminal can be controlled by the current or voltage at a separate terminal. You want to separate the control and the output nodes. You want to isolate, you want to have isolation between them. And one thing we saw is that, well, somehow if we could harness these minority carriers that are injected to the other side, instead of letting them die and kind of disappear in the opposite side, and they recombine eventually with the majority carriers, if you could somehow harness that, we could generate a system. We could create this, maybe we could create a system that did just that, what we wanted to do. And what we saw is that in the case of a BJT, bipolar junction transistor, what we did is that we added a third terminal. So we had a diode, so we had an N. This is an NTN, and you can have a PNP. But so let's talk about the NTN for now. And if you forward bias this junction, so let's call this, we call this emitter because this was where the electrons were emitted, base, and the collector. So we forward bias this junction, VDE, and reverse bias this junction. Let's call this VC. Yeah. And what we had here is that when we forward bias this, we lowered the width of the depletion region between the base and emitter, this depletion region. And we basically lowered the potential barrier here. We saw this in the energy band diagram here. What we had looked like this. So we lowered the potential barrier from where it would have been, and hence allowed these additional electrons to cross and go to the other side. And then what made them go? Again, it's the thermal energy. Now, once they're at the base, what do they see in this simplified picture? They get into the base, and they are still moving randomly, right? So they have the kinetic energy and they move around. And there's a finite probability they make the edge of this second depletion region, where we have between the base and the collector, and it's reverse bias. And so what we have here is electric field. Now, which way is the electric field pointing? We know that we have positive ions on this side and negative ions on that side, so the electric field will be pointing in that direction. So what does it do to the electrons? It sucks them in, right? So once they get close to this electric field, there's no need for additional effort. So they get sucked in, and the way it's shown in the energy band diagram is that we have a large potential barrier because it's a reverse bias junction. So the electrons who make it here, and they randomly make it to this point, they go down this slide and end up in the collector where they are majority carriers again, so you don't have to worry about the recombination. Now, this is the tricky part. This is the danger zone. This is the no man's land, right? For electrons, the base. So you want them to spend the least amount of time in there before, so as many of them as possible make it to the other side, because that's the current, right? The collector current. You want it to be as efficient. You want as many of these guys that are injected or emitted from the emitter side to be collected here. And as few of them as possible lost here. Right? So what do? You make the base as thin as possible. The thinner the better. Okay, in that sense. Now, that's the basic operation, of course. But nonetheless, you still lose some electrons. Why do you lose some electrons here? Because this is the p-type region. There's plenty of holes for them to recombine with. There are minority carriers there. It's the hostile environment for these guys. So they get in there, they're has an efficiency associated with it. So that's a transport efficiency, base transport efficiency, or base transport factor. Alpha T, which is basically the ratio of the electrons that make it to the collector to the electrons that are coming out of the emitter. And we know that this is going to be less than 1. Well, that's one of the things that can happen to that affects total current, right? What are the other things? Well, the electron, in addition to the electrons that you inject from this side to that side, there's something else. You also have holes in the base, right? So these holes are back injected into the emitter. The same thing that happens for the electrons can happen for the holes. I mean, we saw that in the diode, the current had 2 components, the hole current and electron current. So when you lower this potential barrier on this side, there are a whole bunch of new holes that can go. And let's say, for the sake of argument, if the doping levels were the same on this side and that side, what can you say about the number of electrons and the number of holes that are injected? They're on the same order of magnitude, right? Does that make sense? So what we saw last time is that one of the things you could do is to do what? If you want to minimize, ideally these guys are not useful, right? In theory, these guys are not useful because they go into the emitter, but they have no way to be collected again, so they are lost sooner or later. And but this comes off from, this is part of your emitter current. So this part of your emitter current is wasted. So you want to minimize this compared to that part. This component you want to minimize it compared to that. So what we have, this is INE, and this is IPE, right? And then there's an efficiency associated with this process of this injection process, which is called emitter injection efficiency. Shown with gamma, and it's the ratio of these guys, the total base to the total emitter current, which is the sum of the electronic and the hole current. By definition. And of course that's obviously less than 1, but you want it to be as close to 1 as possible. So there are 2 things. Now, we saw that you can control this process by how can we do that? How can we maximize this? How can we make this as close to 1 as possible? You want this component to be as large as possible and this component to be as small as possible. How do you do that? Well, we saw that one way to do that is by having a much higher doping level on the N side than the P side, right? And what does that do? There are a whole lot more electrons per unit volume here than there. What does that do? Well, there's still, when you lower the potential barriers, there are holes and electrons, but now this is multiplied by a much smaller number than this guy, right? So there are much fewer holes to begin with than electrons. There are a lot more electrons to begin with. So you lower the potential, let's say the ratio is, I don't know, 100 to 1. So let's say this is 10 to the 19 per cubic centimeter, and this is the doping level, and this is 10 to the 17 per cubic centimeter. Just to give you an idea of the typical numbers. It can be even higher than that. Nowadays it's actually higher than that. Okay? This is the number of dopants per cubic centimeter. And you can see still, I mean, it's quite small compared to the number of silicon atoms. Even that. And usually but this is considered a very high doping level, so we show it as M+. Now, if you have something like that, approximately, if you lower the potential barrier, you have lowered the potential barrier by the same amount for electrons and holes, right? But how many more electrons approximately do you have to begin? So you lower the potential barrier, there are 100 electrons going this way, and there's only 1 going that way. So you have created a situation where this number is close to 1 by controlling the number of electrons that were available to begin with. That's one way to improve the emitter injection efficiency. Can you think of another way? Can you think of something else that we do? That works, and a lot of transistors are built that way. Can you think of something else, some other trick? we do it this way usually. What we do, we modify the material at the base. So the material at the base has a smaller band gap, which has the same effect as what you just suggested, but from a practical standpoint, that's what we often does. So what if I could make the base material somehow, let's say magically, like kind of engineer the band gap, so it has a smaller band gap, like that, just in the base. What would happen in that case? Well, if it changes the way I've shown it, which if you do it properly, it will. I mean, most of the band gap change falls on this conduction, on the valence band. The electrons won't see any difference, right, in the height of the barrier, right? But the holes see quite a lot of difference because this whole thing gets shifted up. So this thing appears there, and therefore instead of these many, I get only these guys. You say, well, how much difference is that? Remember, this is an exponential dependence. This is an exponential curve. So even a slight change, several tens of millivolts difference in the built-in potential for the holes on electrons can make orders of magnitude difference. So you don't need to make it. Actually, all of these pictures that I'm showing, I mean, of course, it depends on the vertical units, but it's a very exaggerated. All of these differences are on the order of several tens and maybe hundreds of millivolts. Or not several tens of volts on this side at least. I mean, on this side it's 10, quite a few volts. But you need only a slight change, a slight difference between the potential barrier that the holes see and the electrons. That's what we've done, right? We made the potential barrier larger on this side than this side. So it's easier to move from this side to that side, but it's harder to move from the other side to this side. And what that does, it effectively improves your emitter injection efficiency. Yes?
Does that create more problems in the manufacturing process by introducing different materials?
Well, depending on how you do it, it could be a challenge. Let's put it this way. This is, by the way, this is the basis of the so-called heterojunction bipolar transistor, or HBTs. You may have heard the name. This is what HBTs are. Heterojunction because it's as opposed to a homojunction made out of the same kind of semiconductor. The junction is made out of different kinds of semiconductors on the opposite side. And that's why it's called heterojunction transistor, or HBTs. Now, the way it's done, again, it's not that you take a piece of silicon and you take a piece of, I don't know, germanium and put them together, fuse them together and say, oh, okay, I made a heterojunction transistor. What you do, if you, for instance, want to make a silicon germanium transistor, which is very commonly used nowadays, and we do a lot of work with those transistors, is you introduce germanium when you are making the base. You basically make an alloy in the base. So about 20% or 15% of base is germanium as opposed to silicon. So the way you do it is you actually start growing it, then it actually grows. And then when you're growing it, you're introducing germanium. So as it's grown, you have germanium introduced in that part of the transistor. Or, if you have a compound semiconductor, by controlling the ratio of the two components of the compound, or introducing a third element, you can actually create a different kind of semiconductor. So and this whole process is called band gap engineering. Because you're modifying. Now, this is interesting, right? Because if you do this, what does it allow you to do? It allows you to relax this strong ratio, and we'll see why that's important. I'll tell you why it's important, one reason why it's important, right? Because this way, what it tells you is that your emitter side must have a much higher doping concentration than your base side, right? In other words, the base, what can you say about the base resistivity compared to the collector? Oh, the emitter, I'm sorry. The emitter and base. What can you say about the base resistivity? Or the resistance of the base? Let's talk about the resistivity or conductivity.
Base is very high.
It had high resistivity, right? And remember, you want to make the base as thin as possible, so there's a smaller chance for recombination here. When you make it thin, what happens to this resistor? It increases too. So you have a very thin region that has a higher resistivity. So that results in a much larger base resistance, which is not a good thing. Once we get to the circuit design, we'll see why it's not a good thing. Because basically a lot of your signal can fall across that, and you lose a lot of gain. The other thing is that also it's a very sensitive point, because a slight change in this voltage, remember, a slight change in this voltage can result in a substantial change, exponential change in the current, right? Now, if any physical resistor has noise, as we'll see later on. So the noise of this guy directly appears across this junction and modulates its current. So from noise perspective, that's a bad thing too. And we'll talk about this extensively later on when we talk about noise. But so this is an idea. So you don't want a large base resistance. You want as small a base resistance as possible, and this is working exactly against it. Right? For two reasons, of course. I mean, it's exacerbated because of the fact that the base is so thin. So now, if you go to this trick, this HBT trick, it relaxes the requirement of the ratios, right? Because if I can make this Jagerian height larger, then I don't need as low a doping concentration here. So I can increase the doping level here. Maybe I can make it 10 to the 18, just for hypothetically speaking, right? And if I do that, that's a factor of 10 in N, or in P, right? That's a factor of 10 in resistivity. So I've just lowered my base resistance by a factor of 10. Which is a good thing, presumably. So that's one of the advantages of the HBT. Now, the interesting thing is that, so this is a simple picture, right? We said, one of the interesting things is that, I said the electrons go from this side to the other side. Why? Why do they go from one side to the other? Thermal movement, right? Thermal energy. And if that's the case, let me ask you an interesting question. What can you say about the concentration of electrons in the base, namely the minority carriers? So think about the situation that you're dealing with. The situation is that I am injecting electrons from this side at a constant rate, right? Which is controlled by this VB. So I lower the barrier height and they go at this rate, these guys can go. So I'm constantly injecting electrons, minority charge, into the base from this side. It's coming at a constant rate. And then they move randomly, thermally, right, in the base. And every so often they make it to this edge, and once they are here, they're gone, right? They're guaranteed to be collected, because there's electric field and it sucks them in, most of them, a large fraction of them, right? So you have two boundary conditions here. One is that you know that the doping concentration, the electron concentration on this side is fixed, which is controlled by the electronic concentration on the other side. Right? So if you look at it versus distance, at the edge of this depletion region, the emitter depletion region, what I have is that I have some NP, right? Some kind. And I know at the other side, what can I say about the concentration there? I can't have a concentration there, because if I have electrons, it will be sucked in. So the concentration is what? 0. So what can I say about the distribution between these two on the average? What is the How many electrons can I find at some arbitrary point per unit volume in the base? Well, this is one of the things you will find in one of your homework problems. I'm going to tell you what the answer is, but you will still have to do it. The math lab, or a kind of equivalent thing. That's exactly what you do. I'm asking you to say, set a boundary condition that on this age, and you have a fixed number, I think it's 100, right? Particles. And at this age, you have 0. And the other thing is that you assume that at any point you can have a random distribution, but what happens is that there's a 1/2 probability of the electron going to the right, and 1/2 probability of going left for every electron. And you do that, and you let it run, and you see very quickly it converges to something like this, which is not that surprising because it's a so-called diffusion process. So the doping concentration goes, the electronic concentration goes from the maximum to 0 linearly over this distance, and that's just purely because of its random thermal movement in the simplified picture. Okay? Now, again, before I had this argument in my mind, I always thought, well, why should it be like this? I always thought it should be like constant, because electrons are constantly flowing. And what comes into this picture is the random movement and these two boundary conditions. That you have constantly electrons injected on this side, and everything taken out. There's a sink on the other side, and there's a source on this side.
So the assumption is that there's no actual field in the base area?
Yeah, okay, I was about to get to that. So the assumption, exactly, so it's as if I paid you to ask that question. So the assumption so far is that there is no electric field in the base. But is that a valid assumption? Well, not exactly. back to the assumption that this depletion region has very hard boundaries, right? So up to a certain point, you've completely depleted that region of chart, and beyond that, you have nothing. In reality, there are a couple of, first of all, this depletion region is extended, but it's a gradual process, right? So it's not day and night, it's not black and white. So up to this point, you're highly depleted, and then gradually you're reducing the depletion region, right? So this is completely depleted and then gradually. And in this residual part, in this tail, you have still electric field, right? So there is a little bit of electric field. So if I want to show these pictures a little more accurately, what it looks like is that it doesn't really look like this. It looks like it look like that. What does this do? Does this help or hurt this transit process of electrons? It helps, right? Because so this electric field also facilitates the movement of electrons from here. So part of this depletion region is extended, the tail of this depletion region is extended into the base. And that's a good thing, that helps. Now, there's another reason for it. The thing is that the way we actually build these transistors is practically impossible to make a transistor that has uniform doping concentration here, uniform doping concentration here, and uniform doping concentration here. Now, because of the diffusion process and the way it's fabricated and the way we tweak it a little bit, we actually have there's a doping profile in the base itself. So it's not constant all across. And that doping profile leaves these ions behind that create an additional electric field that actually works for you. Even more so. So it's really like this. Which is a good thing, because once you pass this potential barrier, it increases the probability of these guys going through. So in terms of the parameters we've defined, which one of these parameters would that affect? Gamma or alpha T? Which one? Alpha T, right? Because basically, it reduces the time an average electron spends in the base, because the electric field pushes it in that direction. So the less time it spends in the base, the lower the probability of the electron being absorbed or being recombined with the holes. So it improves your alpha T. Okay, so that's good. Okay, so that's for that. Now, so there are other secondary effects that will facilitate this process, so you have to keep them in mind. Now, let me ask you a question. You know, this transistor looks like a two diodes, right? Two p-n junctions back to back. It looks like this, kind of. Well, this transistor looks like that. Right? And you know, when I was in elementary school the first time, I said, "Oh, transistor," and then I said NPN, making kids without quite understanding how the transistor really works. And I said, "Well, this is NPN, and these transistors were expensive." This is expensive. So you know, and I saw some diodes, and two diodes were much cheaper than one transistor. Okay, let me go and buy two diodes and make a transistor for myself. I don't need to buy transistors. And I went to buy two diodes and put them together. And I did this actually. And I tried to replace the transistor in one of the kids. The diode didn't work. Didn't do anything. So, just kind of scratching myself. Well, isn't it just an NPN? And I said, what am I saying? I was looking at it and scratching my head. And I figured that there's something missing, but I didn't quite know what it is. So, can you tell me now? What is the difference between two back-to-back diodes and a transistor? If you actually go and buy two back-to-back, trust me, I've done this. It doesn't work.
A really large base.
That's one problem. True, but say again.
Don't you have metal in between?
Right, you got metal in between. That's even worse than having a thick base. I mean, the thick base is a bad problem, but the problem is that remember what we were doing. We are forward biasing this junction and reverse biasing this junction, right? So let's try exactly the same thing. Forward bias this one, and reverse bias this one. So what will happen? There will be constant current flowing through this guy. And is there any reason for current to flow through this guy? No. So this is off. So no current will flow through here. So all of your current will be flowing between your base and emitter, and no current will be injected into the emitter, into the collector. Why? Because you have this metal. Because when you go from the semiconductor to the metal, all of your minority carriers are recombining. They're gone. The whole operation of this transistor was based on the behavior of the minority carriers in the base. Now, if I put a piece of metal in between, I kill all the minority carriers right there. Like a Minuteman, right?
What if you use like Zener diode and then you exceed the Zener potential?
Okay, well, no, again, that's a secondary effect. But even if you do that, you'll have a second current. So you're saying that if you break it down, right? No junction will last forever. If you apply very large reverse potential, it will break. And so you will have a second current flowing through here that's independent of that current. The key for transistor operation was for making sure that this current, right, is controlled by this voltage. They're completely independent of each other.
What if you use one Zener then?
What say again?
Wait, you're talking? Oh, never mind, that's something useless.
But is it clear what the basic difference is between these two? It's as you pointed out, it's the metal in between that kills it. Other than the fact that the base is very thick, and that wouldn't have been very helpful either. Yes.
So the battery has to be reversed, right? PNP, heavy induction. The VCD.
Yeah, it has to be reverse bias, right? It is reverse bias because this is the end side that we have to put the positive potential applied to. So this junction has to be reverse bias, so there's no net current through this guy, but if you only create the electric field to absorb it. But if you look at it, I mean, in a properly designed transistor, if most of the current, most of the flow of the charge, or most of the electronic current is coming from the emitter to collector, very little of that is going through the base in a properly designed transistor. Right? You want the total alpha, which is the ratio of the collector current to the emitter current, which is the product of the alpha T gamma, to be as close to 1 as possible. Does that make sense? Okay? So that's one thing to keep in mind. Now, but having said all of this thing, one of the things that we saw is that, so well, we have this transistor, okay? And now, what is the current? What is the collector current in terms of the base emitter voltage? Because that's what's controlling it, right? Well, we know it's proportional to the base emitter, to the number of electrons injected into the base by the emitter, right? And what is that number? We know that was proportional to the E to Q VBE over KT minus 1 with some proportionality constant Is. And if you operate the transistor in this mode, we know that VBE is relatively large, right, to carry a reasonable current. So this term is substantially greater than that term. So in forward region, forward mode of operation, it's approximately just this. Because that term is orders of magnitude greater than minus 1. Right? But if you want to keep it in there, then you can keep it in there, but we never do. So this is a very good approximation. As you can see, as we go moving along, there are many approximations we make. And some of them are very good approximations, some of them are okay approximations. This is one of the really good ones. I mean, for all practical purposes, you don't have to worry about that one. Because you can calculate it, right? Assume that the VBE of 0.6 or 0.7 volts supply. Remember, K2 of Q at room temperature is about 25 millivolts. So that's E to the 30 minus 1. Yes. Right. Okay. But if you plot this behavior, this collector current, versus the base emitter voltage, it's an exponential. So if you plot it on a linear scale, it kind of looks like this, depending on the scale. Now, of course, this is an exponential, so there is no real on voltage. But I'm sure anyone who has used the bipolar transistor is familiar with this concept of VBE on, right? The 0.6, 0.7 volts that you need to plug the base emitter voltage to turn it on. So where did that come from? Well, if you look at this graph and plot it on the scale of, let's say, milliamp scale, tens of milliamps or milliamps, what you see is that below 0.6, 0.7 volts for a bipolar, for a silicon transistor, let's say, and this voltage is different for different kind of transistors. For a germanium transistor, it's much lower, it's about 0.3. At that point, basically the current is very small. So arbitrarily, for some of the design aspects of the things that we deal with, you say, well, it's really off below here, and then it's kind of on beyond that. So it's another approximation. Now, this voltage is direct function of what current levels you're dealing with and what IS is. So let's say my IS is for a small signal transistor, let's say an IS of 10 to the minus 15 amps. Right? And let's say I'm operating at 1 millivolt. So IC is 10 to the minus 3. 1 milliamp, sorry. 1 milliamp. So let's say my collector current is about 1 milliamp. Now in that case, what it tells me is that my VBE needs to be KT over Q, natural log of that divided by this. I'm sorry, this divided by that, which is 10 to the 12. Right? And when you do that, what's the natural log of 10? So it's basically, also, and this is at room temperature, this is 25, let's say 26 millivolts, times 12 times natural log of 10. Does anyone remember the natural log of 10? Oh. 10 natural log, 2.3. Okay? So that's around 2.3 times 12 times 26 millivolts. So that's 718 millivolts, or 0.718 volts. Right. So there's nothing magical about 0.6 or 0.7. It has nothing to do with the built-in potential either. Psi naught. Okay? It's just a byproduct of the fact that the numbers are in this orders of magnitude. Now, for a germanium transistor, actually your IS is larger. So it's not going to next to the 10 to the minus 11, 10 to the minus 12. And as a result, this number is smaller for a given current level. Now, milliamps are the typical current levels that we deal with, milliamps and hundreds of microamps, but we typically deal with kind of in small signal electronics. So that's why for many of the circuits that we design, we say, well, you know, you need at least 0.7 volts of forward bias for this to turn on. But that's just a very rough approximation. If you want to know exactly what you need, this is your equation. And many times you use this. But I want you to understand where that 0.7 comes from. Now, if you make a transistor out of a different kind of semiconductor, or if you, for instance, if you have a certain germanium transistor, for them the beyond is about 0.9 volt, for instance, for the typical pattern. And there are all sorts of variations in that, so there's no general rule. And you have to basically deal with it as per case basis, on a per case basis. Okay, so we talked about this, we talked about that, we talked about heterojunctions. Alright, so now we have this picture, right? So let's go and look at the transistor one more time and see what happens to the current flow inside the transistor. See where all the components of the current go. So I like one big BJT. And then we have the forward bias, so this is the N plus, this is the base, this is the E, and this is the vector. And the reverse bias junction, so this is B, CB, VBE, forward bias. And then, of course, so we have the depletion region here. Now, if I were to draw a depletion region here, which side should have more depletion region? Which side does get most of the depletion region, based on what we've said so far? Would most of the depletion region fall on the emitter side or the base side? Base side. Why? Exactly, because we said that we saw that most of the depletion region is dominated by the lightly doped side, because of the conservation of charge, right? The charge on this side and that side have to be the same, and the charge comes from the ionized dopants. So the side that has the smaller concentration of ionized dopants has to be extended farther to compensate for an extension on the other side. So, like that, kind of. And on this side, I show it this way, talk like that. Okay. So now let's see what happens with the electron. So let's look at the chart. Let's follow the electric chart. Now, here, of course, the net current flows which way? Of course, this is a forward bias junction, right? So the current is flowing that way. So the current is flowing this way. Now, what happens? What's the main component of the current? It's the electrons being injected from this side to that side. Now, so let's show that main component of the current with this big arrow. Okay. So I start off with some electrons. So this is a big arrow. Okay. Now, what happens with them? Let's follow them. Let's see what happens. Now, where do they go? What are they spent on? Well, if the transistor is properly designed, most of them make it to the emitter. Those are the successful ones. Good. But how about the unlucky ones? The ones that get caught?
Recombine.
Okay, so a part of that current, the part of that electronic flow goes into the base and gets recombined with what? What does it get recombined with? Holes. Now, if they get recombined with holes, it means that the density of holes is dropping, right? But to maintain a constant density of holes, what needs to happen? You have to replenish the holes. Where do they come from? Second? Battery, right? But more accurately, the base current, right? There's current going to the base, right? And part of that basically accounts for the lost one. Accounts for the lost holes that are lost to compensating the electrons, to capture the electrons. So that's part of it. Okay? And this is what is this process? It's a recombination process. Okay, what else? Now, do I need to provide some additional holes in addition to these? Do I need some more holes?
Yes.
No. Yeah. Right? Why do I need additional holes now? Because still, there will be some holes going injected back into the emitter. Of course, I've played all sorts of tricks. I've lowered the number. I may have changed the band gap, but still there are always electrons that can't have enough energy, or holes that have enough energy to cross the barrier. Just a number that you control. So there will be some that will go this way. So in addition to these guys, there will be a flow like that. And what happens to them? Well, they go to the other side, and then gradually, over time, they recombine. So, but that recombination process can be shown like this. Part of my current goes to that, and a part of it goes to the other side. So this is a recombination in the emitter. They are eventually gone due to recombination, but it's a different recombination at a different place. So this is the part that accounts for gamma, and this is the part that is accounted for alpha T. Now there's actually a third process, which is not very dominant, and I didn't put it in the handout because I like this handout to focus on the dominant effect. You can imagine that even in this case, even if the collector is reverse biased, right? There are still a few holes. Electrons. And there are a few holes that there are a few electrons that are injected like this, back. They go in the base. You get recombined in the base. There are very few. Right? But still, there are some that can go. And they have to recombine with some holes in it. So there's a very tiny component here, the right two. So it's good to know that it is there. It could be there. Now, if your reverse bias on the collector voltage is very small, then they can be substantial. That's taken into account. But for most practical cases, we don't worry about that. Any questions on this? Okay, now, so note so far, this is the model we have for transistor, but this is not a circuit model, right? So let's look at the circuit. By the way, I'm sorry, for one more thing. So you can see here from this picture clearly that it's the base current in a properly designed transistor is to account for these lost poles, and it should be smaller than the collector and the emitter current, right? And the other way to see that is that we know alpha, by definition, is IC over IE. And we also know one more thing. We know that there's conservation of charge. So the total current going into this big transistor thing has to be equal to the total current that comes out of it in steady state, which basically says IB plus IC has to be equal to IE. In other words, now I can plug this into this thing, and we saw last time that you could write basically IC as beta IB, where beta is defined as alpha over minus alpha. You can basically derive it from these two equations. And you can call them alpha DC and beta DC. Just show that. So it says, and beta, you can see that if alpha is close to 1, which is what you want it to be, is a large number. The closer it is, the larger, and you saw it's very sensitive. So if you have the alpha at 0.9, this would be 9. If it's 0.99, it's 99. If it's 0.999, it's about 1,000. Okay? Okay, so having said all of this, how do you model the transistor? Let's look at it and see what we have. So far, we have a diode, right? On the base emitter junction that we care about. And that there's so this is the emitter, this is the base. And what we have here is that we know this current, let's call this IE in this case, is IES. I just show that IS as an IES, VBE over BT. Now, I'm defining BT as KT over Q, which is about 25.8 millivolts at room temperature. Okay? So that's the diode. That's one of the diodes I'm taking into account. But now, in addition to this diode, I have a current source, a dependent current, a voltage, a current-controlled current source. So it's a dependent current source. That's why I show it as a diamond, which basically carries the current, which is alpha IE. And this is the collector. So this is the large signal model for this transistor so far, right? And what it tells you is that you apply voltage here, there will be current flowing in this diode. So this is just a diode. But there's one more thing to it. It's that there's this dependent current source that's controlled by the current of this diode, which is alpha times IE. Now this is called the T model because it looks like a T, right? Kind of a very short stem, but in this case. But other than that, it's like a T. And this is very physical. You see that this is related. This is the injection of electrons into the collector from the emitter. Now, the only reason that all the directions are backwards is that, well, the electronic charge is negative, the way we've defined it. So the current flow is the opposite direction of electronic flow. But other than that, it's very physical. Now, this T model is actually quite good, and we use it very often. This is a large signal T model. But it can be also converted to another kind of model. So let me redraw it slightly differently. So I put my base here, and the diode is the emitter, so this is the emitter. And then I have a current source in the collector, alpha IE, and this is IE. Okay? This is the same model, right? I haven't changed anything, I just changed. That's why we call these, a lot of circuit things topologies, right? Because it doesn't matter exactly how you draw them, as long as they connect them the same way. So now let me play a trick. Do you agree or disagree that if I remove this current source and replace it with one current source of equal value, this node, and another current source of, again, equal value, back to this node, the circuit is exactly the same? So think about it from the perspective of each node. What was the current that this node saw injected by the blue stuff? Alpha IE. 0. What does it see now? 0. What was the current taken out of this node? Alpha E, the same. So they're equivalent, right? The Greek doesn't know agree. I haven't done anything to the equal. Okay, now let's look at that and see. So I remove it and put it here. And I notice one thing. If this is IE, this is alpha IE, right? So that I can replace this whole thing with a different network which carries 1 minus alpha IE, right? So if I change my IS, instead of using that IS, I use my minus 1 minus IE, IES, E2L, whatever, BBE over BT, I'm fine. And I notice one more thing from here. What is IC in terms of BBE? It is alpha times this, which is IES, E2 BBE over BT. Now, this thing is my former IS. Right? I had it somewhere. Right? So that's by definition IS. So IS is alpha IES. So I can rewrite this as what? It's IS over, so this is IS over alpha. So it's 1 minus alpha over alpha, IS, E2 BBE minus over BT. Now what is this quantity? 1 over beta. So this is nothing but IS over beta, E2 BBE over BT. Therefore, I can redraw the model this way. You can say it's a new diode, but now this current, IB, is IS over beta, E2 BBE over BT. And then I have another current source, which is what? Alpha IE, right? But I know IE is what? In terms of, I know this is basically IC, which was beta IB by definition. So this is simply beta IB. So I can rewrite everything now in terms of IB. And this is called a pi model. Looks like a pi. Right? Now, these two are exactly equivalent. Exactly equivalent. So I can take this any time and replace it with that or vice versa. Sometimes it's more convenient to use this guy, sometimes it's convenient to use that guy. So you have two things instead of one you can play with. Now this one captures the essence of the current multiplication. If you control the base current, in effect, you are really controlling the BBE. And through that you're controlling the collector current, which is beta times greater than that. But keep in mind, the real physical phenomenon, the real physical parameter that controls the collector current is not really the base current. Indirectly it is, but directly the BBE. That's why I say this is probably a more physical model. It's closer to physics of the transistor than that. And so that's for that. So let's stop here, take a quick break, and come back. Maybe come back to talk about some other effects in the transistor. And we continue our development of the model and all those things. And then we'll talk about the dynamics of the transistor. Alright? So let's take 5 minutes.